reason of this experiment is a light is electromagnetic wave. Light has dualism characteristic. The both of them are as particle and as a wave. It is as a particle if it haunts another atom, and then it is called as wave if it moves through small rifts. Long time ago, people had an open long time ago, people had an opinion that was light of photon was influenced by amplitude. But Max Planck found a relation in his experiment. The photon was influenced by frequency, and so he also found a constant number, and it called was Planck's of Constante. And then, hence, this experiment will be done to define Planck's of Constante and to define the work function of materials.
In here, I will understand you about photoelectric effect. I will show you about sketch of photoelectric effect. This is a sketch of photoelectric effect. This is a photon. This is electron. This is a plot. Sorry. This is a positive plot, and this is a negative plot. A photoelectric effect is the emission of electron. This is electron when light strike off surface. This effect has numerous practical applications. This attraction causes a potential energy barrier that normally confines the electron inside the material. This is a material, and this is a photon. Think of this barrier as being like a round curve separating a flat straight from a raised sidewalk. The curve will keep a slowly moving score ball in the street. But if the ball is kicked hard enough, it can roll up into the sidewalk, with the work done against the gravitational attraction equal the kinetic energies. This is kinetic energies. Photon to the plot positive, and this is potential barrier, and this is a electron. In Okay, this is a question about photoelectric effect. Hv is photon energy, and Ek is the velocity, energy kinetic or velocity of electron, and this way W is potential barrier in this plot. When photon to the positive plot, electron in positive plot uh, into out to negative plot, and this is Ek is velocity of electron.
Until the time of Isaac Newton, most scientists thought that light consisted of stream of particles emitted by light sources. Galileo and others tried to measure the speed of light. Around 1665, evidence of wave properties of light began to be discovered. By the early 19th century, evidence that light is a wave had grown very persuasive. In 1873, James Clerk Maxwell predicted the existence of electromagnetic waves and calculated their speed of propagation. This development, along with the experimental work of Henry Hertz starting in 1887, conclusively that light is indeed an electromagnetic wave. The wave picture of light is not the whole story, whatever. Several effects associated with emission and absorption of light reveal a particle aspect. In that, the energy carried by light waves is packaged in discrete bundles called photons or quanta. These apparently contradictory wave and particle properties have been reconciled since 1933 with the development of quantum electrodynamics, a comprehensive theory that includes both wave and particle properties. The propagation of light is best described to gain more energy, increasing the stopping potential. But the stopping potential, or we call V0, was found not to depend on intensity. Also, classical physics offers no explanation for the threshold frequency. We found that the intensity of an electromagnetic wave, such as light, does not depend on frequency, so an electron should be able to acquire its needed escape energy from light of any frequency. Thus, there should not be a threshold frequency we call V0. Finally, we will expect it to take a while for an electron to collect enough energy from extremely faint light. But experiment also shows that electrons are emitted as soon as any light with V or frequency is larger or equal with V0 hits the surface. The correct analysis of the photoelectric effect was developed by Albert Einstein in 1905. Building on an assumption made 5 years earlier by Max Planck, Einstein postulated that a beam of light consists of small packages of energy called photons or quanta. The energy A of a photon is equal to a constant h, or Konstanta Planck, times its frequency f. From f is c per lambda for electromagnetic waves in vacuum. We have a Planck constant is 6.6260693.
Result the experiment is
Yuk.
data which gained in the experiment are voltage and current.
Yuk.
The variation in the experiment are like sensitivity, like intensity, and filter color. For one color filter, we use variation for uh, intensity variation and 2 sensitivity variation. And here are our data.
From the data we get, we can make a graphic like this. From the data and the graphics, we can conclude that the intensity has an effect in the value of current that produced. And this current will have, so we can say that more intensity will produce more energy. This is happening because when the intensity of light is big, we can say that the photon from that intensity of light is big too. So when the intensity is more big, the voltage that produced is more big too. So the intensity have effect on the energy. So we can say that more intensity will produce more energy. This process is matched with the photoelectric effect that the photons distribution, it depends on the light intensity that produced. And the other, on the experiment, we can know that the sensitivity has effect on this experiment. More sensitivity will produce less current. So when the current is more or less the voltage will be low, and that the so from the sensitivity connection with the current, we know that less current will be less voltage. From the filter fluorescence that we use, we know that when we use the blue filter will produce most current. After that, the green filter will be less than blue filter. So, and the last is the red filter that has uh, at that has least current. This is happen when we use two variation of sensitivity and intensity variation. This make this is has is this is the effect of the long wave. That from the graphic we know that more long wave will produce more voltage. This is connected with the photoelectric effect that state that the energy that produced is not depend on the light intensity but depends on the long wave.
Conclusion. Based on Planck constant experiments that have been performed, can be concluded that the value of Planck constant to 0.1 mA sensitivity is equal to 4.61 q-second, and for a sensitivity of 1 mA is equal to 3.49 q-second. As well known, work function is also great for 0.1 mA sensitivity is 0.77 electrovolt, and for the sensitivity of 1 mA is 0.64 electrovolt. As well known, work function is also great for 0.1 mA sensitivity is 0.77 electrovolt, and for the sensitivity of 1 mA is 0.64 electrovolt. The author acknowledgement. The author would like to thank to laboratory assistant Puspita Arumsari, M. Nasrullah, Aris Widodo, and Rido Fajirahman has quite the Planck constant experiment. Do not forget to thank to friend of the team for a corporation is doing the lab. Reference 1. This reference of this experiment 1. Tipler Physics for Science and Engineering 2. Halide Resnick Modern Physics, and the last Kenneth S. Crane Modern Physics. Thank you.